In this video, we're going to talk about a very special case of conservation of momentum called impact. Right? So impact is just when we have two bodies or two particles that collide during a very short period of time that causes these super large impulsive forces between the bodies. Right? So impact is just the interaction of those two bodies colliding, and this is a special case of our conservation of momentum. Conservation of momentum. And with this, we usually see two different types of impact. There are two ways that these two particles can kind of hit each other. One is that we have two particles that are coming towards each other and they impact coming into a straight line with each other. Right? So we have two particles. They impact and they act on this like line of impact. So our particles A and B, they act on this line of impact. They linearly come and touch each other. They collide there. This we call central impact. So they're right in line with each other, straight in a straight line. An example of this might be when you strike a hammer on a nail, right? So you have the nail, the hammer comes straight down and impacts on that nail. That would be central impact. The other case that we can see with impact is when we have two particles colliding that aren't necessarily coming in on straight lines with each other. They're not like in line with each other necessarily. So maybe we have one particle, let me draw it this way, one particle coming like in from the left and then up and in from the right, where the way that they're impacting is they're kind of coming at each other at an angle, and they kind of hit off of each other and then go out at angles. So you might see this a lot with, like, if you've ever played pool, if you've ever played billiards. This is a lot of times how billiard balls will kind of knock against each other. If there's a lot of different balls on the field, they might come in at different angles like that. Or like knocking off of a wall or something like that. So this, when we have two particles impacting, but they're not coming in at this straight line. Instead, these forces, their velocities, they're coming in kind of at an angle, and they intersect at this plane of contact. Instead, we call this oblique. I don't know why I decided to write this all caps, but this is oblique impact. So central impact, they act right on that central line of impact. And then oblique impact, they act on this plane of contact is where they really come together. And we can still use like a line of impact for reference here and get angles between where these velocities are coming in at and where those particles are contacting each other relative to that line of impact. So these are our two main types. We have our central impact, we're acting completely in one linear direction. Oblique impact, we usually have x and y components of our velocity. We're kind of acting at an angle, and they're contacting each other at a plane and then going off their own ways. So how we define these impacts, like how we kind of classify them, might feel familiar to you. So back in physics classes, we often describe these impacts, these collisions, as being perfectly elastic or inelastic or plastic collisions. So you might have seen these terms before. You might be somewhat familiar with them. Perfectly elastic, inelastic, and plastic. So perfectly elastic means that the two particles are coming together, they're impacting, and then they're bouncing off of each other with no energy lost whatsoever. This is in a perfect world, never really happens in reality. Perfectly elastic, all energy is conserved. So let me say it this way, no energy lost. Bounce off each other. Then for our inelastic collisions, we describe those as they do bounce off of each other, but some of the energy is lost. So they bounce off each other. Some energy is lost. And then finally we have plastic collisions. And for plastic impact, that means that they are sticking together, right? They are impacting, they are colliding, and they are stuck together, and they are moving in some direction together after that. So particles stick together. But where do these come from? How do we classify things as perfectly elastic or inelastic or plastic? And what do we do with that? These classifications come from something called the coefficient of restitution. And this is how much our particles can deform and then go back into shape as they collide with each other. How much do they collide, deform, go back into shape when they go through that impact? Are they losing any energy when they're impacting with each other? And so this is defined by our coefficient coefficient of restitution. And the coefficient of restitution is represented by the letter E, just like a lowercase letter E. And it is defined by the velocity of B final minus the velocity of A final over the initial velocity of A minus the initial velocity of B. So what it is it's a ratio of the relative velocities. Right? On the top here we have the relative velocity after impact. Right? It's the after. So it's the relative velocity just after impact over the relative velocity of those two particles, relative velocity before impact. So those ratios of velocities can kind of tell us how much energy is being lost when those two particles are colliding with each other. And those E values, those coefficient of restitution values, define these perfectly elastic, inelastic, and plastic conditions. So perfectly elastic means that our coefficient of restitution is 1. Everything was perfectly conserved. They just bounced off of each other, no energy lost, kept doing their own thing. Not realistic. This does not happen in reality. Things are not perfectly elastic in the real world. But it is good to know, right? It's good to know that if something is perfectly elastic, it would have a coefficient of restitution of 1. Then in our world, what we're going to see a lot more often is stuff behaving inelastically. So it could be elastic, like not perfectly elastic, ranging somewhere in that bouncing off of each other, but energy is lost, is where we have, not equals. 0 is less than our coefficient of restitution is less than 1. It falls somewhere in that 0 to 1 range. And then if we have plastic impact where they're sticking together, there is no coefficient of restitution. That coefficient of restitution is 0 because they never restored themselves back to two individual particles. Instead, they came together as one. Particles stuck together. So that coefficient of restitution is 0. And you'll notice for all of these, our E value is always going to be between 0 and 1. It could be 0, it could be 1 in these problems that we work as we're kind of learning what this coefficient of restitution is and how we use it. But it's always going to be in that range. So if you're ever calculating one and you get something outside of that range, it's a pretty good indicator that something has gone a little bit off. But more often than not, coefficients of restitution are given to you in your problem statements because these things are derived experimentally. They're derived from data sets for certain materials, and that's how we know what our coefficients of restitution are for certain materials, situations, etc. So typically your problems will be giving you a coefficient of restitution for how something is going to behave in that impact, in that collision. And that's what we'll use to kind of typically figure out final velocities. This is usually what we're doing when we're dealing with these conservation of momentum problems. And again, impact, it's just a special case of conservation of momentum. So it's just another equation that we can use to relate our final velocities together to solve for those final velocities. That's almost always what we're trying to find in these kinds of problems. So just as another example, kind of explaining this coefficient of restitution just a little bit more, like what this really means dynamically and for all of these forces and everything, is when we have these two particles that are going to collide. What happens is that these two particles come together and they deform. Right? So they have this impulse on each other. A is affecting B, B is affecting A, and they deform. They go through this deformation until they squish together to a maximum deformation, and then they come out of that with a restitution impulse. So we go through a deformation impulse, those two forces acting on each other, and those forces act back out in this restitution impulse, and they start traveling on their own ways again. So not only is it this representation of this ratio of relative velocities before and after, but really the definition of our coefficient of restitution is the ratio of this restitution impulse to this deformation impulse. So it's how much of that deformation is it really recovering, because some of the energy is lost from this process of deformation and restoring itself, right? Going through this restitution. So that's really where this E is coming from. It's really coming from this restitution impulse as a ratio to the deformation impulse. But for our purposes, we usually just use this more simplified form, you know, with already having the integrals done and relationships done and everything, which is just those ratios of relative velocities after to relative velocity before impact. So this is our equation we'll be using most often for our coefficient of restitution. And we can see, you know, it may be a little bit hard to see that these particles do kind of squish against each other and then come back out, but if we ever watch like a slow-mo video of an impact, we can actually see this effect of these particles coming together and then coming back apart where they're squishing against each other. And there's lots of really great, you know, videos on YouTube of this impact. Here's one that I found earlier that I thought was a really good demonstration.
Oh, God.
So you can see in this slow-mo, you can see both the face and the ball deforming as they impact each other. The face deforms and the ball. Both are deforming. They're kind of losing that curve shape there.
Look at this. I reckon.
Right, and then you can see the ball almost floats in midair here as all of the momentum is transferred to the head. So we can really see kind of how this deformation and this impulse and this conservation of momentum is working in real life. So now that we have this new kind of equation, this new relationship with this coefficient of restitution, we can use this to solve impact problems. And again, those two main types of impact that we're going to look at are central impact and oblique impact. So before we actually solve a problem for central impact, let's talk about some tips to make it easier to solve these problems and some guidelines to use as you're working through a central impact problem. So the first thing that we want to do with these impact problems is it's really, really important for us to set the positive direction of velocity. Right, so we want to establish the positive direction for our velocities. And the reason this is really important is because the positive for both particles, the two particles that are impacting, need to be the same positive direction. It doesn't mean that the particles need to be traveling in the same direction. It just means their positives, their coordinate system needs to be the same. Right, so establish positive direction for velocities for both particles. Same direction. Right, because we're working now with this system of equations where we want to make sure we're having consistent sign directions between these velocities. And it can help to draw velocity diagrams for what the velocities are just before and just after impact. Right, those are the velocities that are going into the coefficient of restitution, are the velocities just before, like just the split second before impact and just the split second after the impact occurs. So establish our positive direction for velocities for both particles. Say diagrams can be helpful. And then from there, we're going to want to apply both of our equations. So remember, this is a special case of conservation of momentum. So we're going to apply our conservation of momentum. Sum of masses times sum of velocities initial, equals sum of masses times sum of velocities final. And this is going to be in one single direction, right? So this is along the line of impact. Then we're going to apply our coefficient of restitution. So now we're going to use that coefficient of restitution, which is VB2 minus VA2 over VA1, minus B1, again, is those relative velocities of the after and the before for a coefficient of restitution for this. And usually these two equations are going to be enough to get you to solve the problem. But if there's something else you're missing, maybe there's maybe you don't have an initial velocity, maybe you don't have velocities at all, you have positions and accelerations and things like that. Maybe you have to do a little bit of legwork to find initial velocities. You can also always use our kinematics or work and energy or F equals m, any of the other concepts that we've talked about so far to get where you need to go. Right? So just keep that in the back of your mind. I'll put that as 4, as use kinematics or work, energy, blah, 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 etc. as needed. So just keep in the back of your mind that those are always there for you. They're always available. It's just a matter of picking which ones you might need, which ones you might want to use to solve your problem. So with that, let's go ahead and do an example of solving a central impact problem. Alright, so in this example, we have a bag A having a weight of 6 pounds, is released from rest at the position theta equals 0 as shown in this image. After falling theta equals 90 degrees, it strikes an 18-pound box B. If the coefficient of restitution between the bag and the box is E equals 0.5, determine the velocities of the bag and the box just after impact. What is the loss of energy during collision? All right, so let's think about the physics, everything that's happening here, as we kind of try to figure out this impact problem. We know it's going to be an impact problem. One is that our image is very helpful and tells us there's a line of impact. But we know that because our bag is going to hit this box, right? They're gonna impact each other. What we don't know is how fast that bag is going right before impact. So when we're doing these impact problems and using this coefficient of restitution and conservation of momentum, the big key is that those velocities we're looking at are right before and right after impact. So we're not using the initial velocity of the bag being 0 because that is not right before impact. Right? We need that velocity that is right before impact in order to do these problems. So what I have is I have this initial setup where I have bag in the air and box on the ground. But I want to look at my just before impact scenario. So just before impact, we have the box and the bag. And the box is just sitting there, right? The box isn't moving just before impact. So VB is going to be 0. It's not moving at all. But our bag is, right? Our bag, A, is swinging in with some initial velocity. And we don't know what that is. And then I'm going to just for reference, I'm also going to draw my just after impact scenario. So just after impact, we're going to have our box. That is now moving. We're going to assume it's moving to the left. And I'm also going to assume that my bag is moving to the left too. I don't actually know if either of those are true. But kind of based on the way that it's moving and the way that this thing is going to hit it. VB2, we don't know what it is. And VA2, we don't know what that is. And so we're trying to find those velocities of the bag and the box just after impact. So those are our goals. So again, first thing we said that we were going to do is establish what's positive. And in looking at the way we've analyzed this, the way we've said, okay, this is what's just before impact, this is what's just after, it looks like everything is going to be moving to the left. So really it would make more sense to go ahead and set to the left as my positive velocity. Right? Set to the left as my positive convention because everybody's moving that way anyways. Why make everything negative when I could just make it all positive? So I'm going to assume my left is positive. I'm going to assume everybody's moving to the left. And then I come up on this guy right here. Right? I don't actually know what that velocity is right before impact. But I know that I have a whole bunch of other equations in my tool belt that I can use to figure out what that speed is if A, the bag at A comes from rest and swings down here. And for me, if I was looking at this and trying to figure out what to use, I think I would probably go with a conservation of energy in this one. Right? If I start out at the top and I just I just release it from rest at A, the only thing doing any work is the weight of the bag. So I would think, conservation of energy would be a really good one to determine what that initial velocity is. So again, conservation of energy is going to be initial kinetic energy plus initial potential energy equals final kinetic energy plus final potential energy. And I'm going to call this up in the air. This right here is 1, my initial, and then right before it hits the box, we're going to call that 2. And trying to think, is there anything else that I need? Oh, I need a datum. I think I'll say that my line of impact here is also my datum for where potential energy is 0. So what that's going to give me is an initial kinetic energy, 1/2 mv1 squared, plus my initial potential energy, which I'm going to have W times Y equals 1/2 mv2 squared, plus my final potential energy, and since of course I'm down at the datum, that's going to be 0. And I could have written out my initial kinetic energy too, right? My initial velocity is 0 there at the top. There is no velocity, so there's no initial kinetic energy. So all I have is Wy equals 1/2 mv2 squared. So my weight is 6 pounds. My height there is 3 feet. And that's going to equal 1/2 times the mass. Mass, of course, when we're working in our US units, you have to divide the weight by 32.2. So 6 over 32.2. V2 squared. When I pop that into the calculator, I get a velocity of 13.9 feet per second. And this guy is our initial velocity A1, VA1. So now that we've done all of that work, we can actually start the conservation of momentum and impact and the coefficient of restitution part of all of this to find those final velocities, right? That's really what we're interested in, is those final velocities. So now I've got all my setup. I'm going to go ahead and apply my conservation of momentum first. So let's do orange, I guess. So conservation of momentum, that's my MAVA1 plus MBVB1 equals MAVA2 plus MBVB2. Just added just those initial momentum equal final momentum for those two. Again, they're colliding. We're going to assume they're not sticking together. It's not a sticky bag. It looks like a sand bag. So we're going to assume they're not sticking together there at the end. And I'm going to start plugging stuff in. So my initial mass of A, 6 over 32.2 times the velocity A1, we just found that, 13.9, plus initial mass and velocity of B. There is no initial velocity of B, it's not moving. That's a big fat goose egg, that's a 0. Equals MA, which is 6 over 32.2 times VA2 plus MB, and what did we say the mass of this box was? 18 pounds. 18 over 32.2 times VB2. Which is a good start, right? I can simplify this down a little bit if I really want to, and I can say 13.9 equals 3 VB2 plus VA2. Right, essentially I had just canceled out all of the 6 over 32s because every single one of these has a 6 over 32 in it. So I canceled all those out, just simplified it down a little bit before I move on to my coefficient of restitution. So my coefficient of restitution is what gives us the other relationship here. And so for those velocities in the x direction, I'm going to have VB2 minus VA2 over VA1 minus VB1. And they gave us a coefficient of restitution of 0.5. I have 0.5 equals VB2 minus VA2 over our VA1 is 13.9 and VB1, initial B velocity, is 0. So that's going to give me a relationship for this A and B. Whoops. Sorry. Where I can multiply that over if I want. 6.95 equals VB2 minus VA2. And then I can start just doing some substitutions. Right, so if I rearrange this guy for VA2 equals 13.9 minus 3 VB2 and plug this into here, I can go ahead and solve for VB2. $6.95 equals VB2 minus 13.9 minus 3 VB2. And when I punch that into my calculator and simplify it, I get my velocity of B2 is a positive 5.21 feet per second. So that means that it is moving to the left, because we said our left was positive. So the box is now moving to the left by 5.21 feet per second. And back plugging in over here, I'm going to get my VA2, so the speed of the bag after impact is a negative 1.74 feet per second. So it meant I assumed the wrong direction. A actually is not going to continue swinging swinging towards the box after it hits the box. Instead, it's actually going to ricochet off and start moving to the right. So that bag bounces off the box and moves to the right. So that's how we get our final velocities for this guy. But it did have one more interesting little bit on here, where it asked us, what is this loss of energy during this collision? What is the loss of energy during that collision? So if we think about what does that mean? What is it asking us? Loss of energy during collision. That loss of energy is any work that we can't account for. Right? So if it was perfectly elastic, then all of our energy would be conserved and we could use conservation of energy, but it's not. And since we have non-conservative forces, forces where energy is lost, it is not conserved. What this means is that we can use our work energy principle, rearranged just a little bit to find this energy loss. So our energy loss is actually going to be those non-conservative forces, the work from those non-conservative forces. That is the energy that is lost. The work of non-conservative forces is T2 minus T1, and that's that final kinetic energy minus initial kinetic energy. So to find this energy loss, my initial kinetic energy is going to be 1/2 ma va1 squared. And then we know the box has no initial kinetic energy, so I'm not even gonna waste our time with that one. Minus our final kinetic, oh, I have these backwards, sorry. Our final kinetic energies minus our initial. So our final kinetic energies, m of our bag, v of our bag, of our box, final, 1/2 mv squared, minus initial. Sorry, I got it a little twisted. So final kinetic energy of A plus final kinetic energy of B minus initial kinetic energy just of A, because B has no initial kinetic energy, it was at rest. So all I'm doing is popping numbers into this energy loss equation. 1/2 times mass of A was 6/32.2 times my VA2 squared, we just found that, negative 1.74 squared, plus 1/2 MB is 18/32.2 times VB2, 5.21 squared, minus 1/2 times 6/32.2 times initial speed was 13.9 feet per second. That is squared. And it's just punching all of that into the calculator. Notice that nothing here cancels. This doesn't equal 0. We're just punching this into the calculator to find this energy loss. And this energy loss from our calculator is negative 10.1 pound-feet. Right? A negative is what we expect. We expect a negative because it is a loss. Right? If it were positive, it would have meant that the system was gaining energy somehow, which it's not. So from this impact, we lost 10.1 pound-feet of energy. So much like we did for central impact, let's talk about some tips for solving the oblique impact problems. And so now remember, with an oblique impact problem, what we have is two particles that are coming together that aren't coming together on a line necessarily. They don't have a direct line of impact, but they're coming together on this plane of impact. They're kind of meeting in the middle, where from a line of impact perspective, they're flared out, each one at an angle, when they're coming together in this oblique impact. So that means there's a little bit more to account for in these oblique impact problems than there were for the central impact problems, because you're going to need to account for both the x and y directions of velocity. You're not acting just on a single line, not acting just on the line of impact. You have velocities in the y direction and in the x direction that have to be accounted for. So with these, you're going to still start it the same way that you want to start your central impact problem, by establishing those positive directions for velocity. So establish positive directions. Direction for velocity. But now keep in mind, you need to do this for the x and y directions. Right, so two directions now. Two directions. Establish both. Keep it consistent for both particles. Keep consistent for both particles. Now your second step, much like our central impact, will be applying our conservation of momentum, but we're going to start with conserving our momentum along the x-axis. So momentum is conserved along the x-axis. Momentum conserved on line of impact. And it could be wherever the line of impact is. It's typically the x-axis. So momentum is conserved on the line of impacts for the x-axis, so that means we're doing our sum of mass initial times velocity in the x direction, initial, equals sum of final masses times velocity in the x direction, those final velocities. Also with that, the coefficient of restitution only acts on the line of impact. It does not act on the y-axis. It does not act on your like plane of contact. Your coefficient of restitution only acts along line of impact. Again, typically your x-axis. So in this case, it's going to be those coefficient of restitution is going to be VBX component 2 minus VAX component 2 all over VAX component initial minus VBX component initial. Right, so coefficient of restitution only acts along the line of impact on our x-axis. You do not need to account for it for the y-axis. What we do need to account for our y-axis is knowing that momentum is still conserved. Momentum will be conserved for the y-axis, and since there's no coefficient of restitution, really it's acting kind of perfectly elastic in that way, in that y direction. Momentum is conserved. Along the y-axis for both particles. And what this means, since the coefficient of restitution really has nothing to do with our y-axis, if our masses are unchanged, and in our impact our masses are going to be unchanged when they collide with each other and then come off, it means that for our y direction, our initial velocity in the y direction will be the final velocity in the y direction. So VAY1 will be VAY2, and VBY1 will be VBY2. So the y components of the velocity for a particular particle will be the same, both initial and final. No change there. So with these kind of tips and I guess things to be aware of in mind, let's take a look at an example of oblique impact. Alright, so here we've got a problem with oblique impact, which we can tell because they're kind of coming at each other at two different angles, right? The way that they're hitting each other isn't exactly lining up. So we have two smooth disks A and B that have a mass of 1 kilogram and 2 kilogram respectively, sliding on the horizontal plane and colliding with the velocity shown. If the coefficient of restitution for these disks is E equals 0.75, determine the x and y components of the final velocity for each disk just after collision. So again, with these oblique impact ones, what we're really going to want to do is establish our positives, break everything into x and y components, and then solve with our x-specific equations and our y-specific equations. So I'm just going to use the positive convention that they kind of gave me here and just say that my positive y is in the positive y direction and my positive x velocity is in the positive x direction. I don't have a reason to overcomplicate it more than that. I'm just going to keep things nice and simple. And then I'm going to go ahead and I'm going to break these down into their x and y components. So we have disk A is the smaller one on the left here, and it said that this was 1 kilogram. I'll go ahead and note that on here. 1 kilogram, and then it said this guy was 2 kilograms. And I have my VA1 is 3 meters per second, and it's acting at a 30-degree angle from like our x-axis, our x like line of impact. And then we have VB, and it's acting at 45 degrees from our x-axis. So let's just break them down into their x and y components. So VAX1, the x component of this guy is going to be 3 meters per second times cosine 30. And that seems to be in our positive x direction, so I can pop that into the calculator and get 2.6 meters per second. And then I'll look at my y component for this guy. VAY1, that's going to be 3 sine 30. And again, that's in the positive y direction, so that's a positive 1.5 meters per second. And then we'll do it for B. For VBX1, this time I've got a 45-degree angle. 1 times cosine 45. But notice this velocity is pointing in the negative x direction, so this is actually going to be a negative 0.71 meters per second. And then for VBY1, again, another negative in the y direction. Sine 45 is negative 7.1 meters per second. So now that I have all of those components, what I'm going to do is I'm going to do my x-axis first. X-axis equations first. Right, so conservation of momentum and coefficient of restitution. Both of those apply for my x-axis. So first things first, let's do conservation of momentum. Momentum, x-axis. And so that's going to be ma times max1, right? So initial velocity in the x direction, plus mb times vbx1. Those are my initial momentum for A and B, equals the final momentum, and we're going to assume that they just bounce off of each other. ma v a x component 2 plus mb vbx2. Right, so here I have two unknowns. Right, I know that I'm going to end up with 4 unknowns total, 4 things I'm solving for, because I want to find the x and y components of the final velocity. 2 final velocities, an x and y direction, 2 times 2 is 4. So I'm going to go ahead and pop in what I know in here, and that's going to be my mass is 1 kilogram times VAX we said was 2.6 plus 2 kilograms times negative 0.71 equals 1 times VAX2 plus 2 times VBX2. In this case, I'm not going to even assume I know where these are going. I'm just going to assume everything is going in the positive direction, positive x direction, until the signs tell me otherwise. And so we can already see I've kind of hit a stopping point in this one. I'm going to need another equation to work with. So I'm going to swap over to my next step and do my coefficient of restitution, because this only works in the x-axis, right? It only works on the line of impact. So my coefficient of restitution is going to be VBX2 minus VAX2 over VAX1 minus VBX1. And the coefficient of restitution they gave was 0.75. So 0.75 equals VBX2 minus VAX2 all over 2.6 minus a negative 0.71. So now I've got these two relationships, these two equations, I can plug into my calculator and solve. Right? 2 unknowns, 2 equations. I would probably solve for this AX term in the green equation and plug it in over here to solve for my VBX. But I will spare you the details on that and tell you that our final velocity for VBX2 is a positive 1.22 meters per second. So it was positive. It is moving to the right for this one. And then our VAX2 came out with a negative number. So A is moving in the negative x direction, 1.26 meters per second to the left. And you can really do it either way. If you want to make it just negative and not do these sign arrows, you can do it either way. I like to indicate directional arrows, but either way, it's communicated clearly, whether you're using your signs or you're using directional arrows. Both are pretty clear. All right, very last step here. We found our x components of velocities. Now we just need the final y components of velocities. So our momentum is conserved in the y direction. Momentum conserved in the y direction as well. And since their masses aren't changing, what we get is that VAY1 equals VAY2 and VBY1 equals VBY2, which really means we already have our answers for our y components of these guys. They do not change. VAY2 is going to be 1.5 meters per second. And of course that was positive, so it's still going up. And VBY2 is going to be negative 0.71 meters per second. So it is moving down. So what that looks like is that when A comes in and bumps off of this, it goes up out like that. And then when B does the same, B comes in, this bounces off, goes out in some direction like that. So we found all of our components of our velocity, which is usually our goal, finding those final velocities using this coefficient of restitution and our relationship with conservation of momentum, determining like our specific type of impact to solve these problems.